I wanted to go over the derivation of how to do the complex eigenvalue case again. So again, we're at the point where we have lambda is equal to alpha plus or minus beta I, just by using our formula that we've had before for just plugging this into an e to the constant times t formula. We would notice that our general solution, if we did it that way, would be a c1 k1 e to the alpha plus beta I times t plus c2 k2 e to the alpha minus beta I t. Now, from the stuff that we saw in class, we can actually replace this k2 with a k1 bar. Remember, the bar means conjugate. Our eigenvectors for complex conjugate eigenvalues are actually complex conjugates as well as eigenvectors. So let's ignore, again, remember that these constants here mean that we're actually doing any linear combination of these two solutions. And in general, if we have two solutions to a homogeneous equation, remember that we can always get another solution by any linear combination that we want. So in particular, we're going to write these in a better form so that we can see a more general solution. So let's say we look at our first solution, ignoring the c's for the time being. Let's say we did 1/2 of k1 e to the alpha plus beta I t plus k2 let's make it k1 bar e to the alpha minus beta I t. So in this case, we know that our e to the alpha plus beta I t is e to the alpha t cosine of beta t plus I sine of beta t, and then plus k1 bar e to the alpha t, and this will be cosine of beta t minus I sine of beta t. Remember again that this minus sign here would get put in the arguments for these two functions, but cosine is an even function, so the negative can just go away, and the sign is odd, so we can actually just pull the negative out in front. Notice in this case when we add, this turns out to be 1/2 times k1 plus k1 bar e to the alpha t cosine of beta t, and then plus 1/2 of k1 plus k1 bar e to the alpha t times I sine of beta t. Let's do a similar thing for x2. If we do I over 2 times k1 e to the alpha plus beta I t plus k1 bar e to the alpha minus beta I t, this is I over 2, times, let me put a negative in front of this k1 because I want to do a subtraction idea here. So this would be negative k1 e to the alpha t cosine of beta t plus I sine of beta t plus k1 bar e to the alpha t cosine of beta t minus I sine of beta t. Notice the idea behind putting this negative in front of the k1 is basically to try to get the other ones to cancel out, if you will. Pardon me. All right, so if we look at this rearrangement here, we can do, this is negative I over 2 times k1 e to the, let's factor this out, and k1 minus k1 bar e to the alpha t cosine of beta t, and then this will be plus I over 2 negative k1 minus, or yeah, minus k1 bar e to the alpha t times I sine of beta t. So I could have factored that negative out in front as well. All right, so let's look at this real quick. Notice I have an I here, so I'm just going to put it out here this way. We'll write this as, so your x1, if we rewrite it, that's 1/2 k1 plus k1 bar e to the alpha t cosine of beta t, and then plus I over 2 k1 plus k1 bar e to the alpha t sorry, not I anymore, sine of beta t. And I believe I missed a sign. This should actually be a minus sign here. My apologies. That should be a minus up here because of this minus right here, which means that this should be a minus here. Okay. Now let's look at your x2. We've got, I'm just going to rearrange the order. I'm going to write this one second. Minus I over 2 k1 minus k1 bar e to the alpha t cosine beta t. And then we'll have, notice we have I times I is I squared. I can factor out the negative there as well. So I actually get a positive 1/2 k1 plus k1 bar e to the alpha t sine of beta t. All right. So now let's look at these two parts. This part here, if I add complex conjugates, the imaginary part goes away. I get 2 times the real part, so this is times 1/2. So we get just the real part here. And notice it's the same one in both of these places here. Look at that. We've got the same exact coefficient on each of those terms. And then the same idea here. If I do k1 minus k1 bar, pardon me, times I over 2, I get the imaginary part. And these these are essentially the same thing except for the minus sign. So what we end up with here is, if I say B1 is 1/2 times K1 plus K1 bar, and B2 is I over 2 times K1, negative K1 plus K1 bar, this leads us to that theorem that we had that gave us our solutions that our x1 will be b1 cosine of beta t minus b2 sine of beta t times e to the alpha t, and our x2 will be b1, or b2, pardon me, cosine of beta t plus b1 sine of beta t times e to the alpha t. So it's doing that what we refer to as the superposition principle, basically that the sum of 2 solutions is another solution, to get us to the 2 solutions that we want, that get us rid of the i's. That's the important part, is we're getting rid of the i's. The b here again is our real part of the eigenvector corresponding to alpha plus beta I, and b2 is the imaginary part. So let's see if we can do one of these. Let's look at, I'm going to look at number 40. This is on page 325. We have x prime is equal to 2x plus y plus 2z. Y prime is 3x plus 6z. And z prime is negative 4x minus 3z. Our matrix will be 2, 1, 2. 3, 0, 6, negative 4, 0, negative 3. Now we can use Geogebra to help us get all of the stuff that we want. So let's flip over to Geogebra. Let's turn on the CIS menu, and let's turn off the graphics and put on the spreadsheet. Type in our matrix, 2, 1, 2, 3, whoops, 0, 6, and negative 4, 0, negative 3. And we'll go over here and tell it to define a matrix. We'll call it A. Define a new matrix B to be A minus X times the 3 by 3 identity. We want the determinant of that matrix. And since I know we're going to be ending up with some complex eigenvalues, let's go ahead and do C-solve of that equation, or that's polynomial equal to 0. There we go. So we're going to have a solution. A solution here that corresponds to a real eigenvalue, and we can find the eigenvector associated with that and write the solution, and then we got complex eigenvalues, and we can get those solutions as well. So first, let's substitute into B. We want to change the x into a negative 3, and we want to reduce row echelon form of number 4. So that gives us an eigenvector of 0, negative 2, 1. So for our lambda equal to negative 3, we get an eigenvector of 0, negative 2, 1. We also had our other eigenvalues were 1 plus or minus 2i. So we need to do the B1 and the B2 for those. Remember, that's our real part and imaginary part of the eigenvectors associated with the 1 plus 2i root. So let's do and substitute into number, I want to substitute 1 plus 2i, and don't forget to hit the alt with the I, and then reduced row echelon form of number 6, and we get that. So we've got an eigenvector here of negative 1 minus I over 2, and a negative 3 halves I, 1. So let's write that down. We had negative 1 minus I over 2, negative 3i over 2, and 1. We want the real and the imaginary parts. So the real parts here are negative 1, 0, 1. And the imaginary parts here are negative 1 half, negative 3 halves, 0. So now we're ready to write our general solution. Our x will be C1 times the K1, 0, negative 2, 1, and that's e to the negative 3t. And we'll get a plus C2 times, and this is where we're going to use our new formula. We'll have B1, which is negative 1, 0, 1, cosine of 2t, 2 again because our beta is 2 over here, minus negative 1 half, negative 3 halves, 0, sine of 2t. And that whole thing will be times e to the t because our alpha is 1. And then our other linearly independent piece that we need will be the B2, negative 1 half, negative 3 halves, 0 times cosine of 2t, and it'll be plus negative 1, 0, 1 sine of 2t, and that's e to the t as well on the outside. So that gives us the solution to that particular problem for a complex eigenvalues. Hopefully that was a little bit clearer. I'm not necessarily sure it was, but hopefully it was a little bit clearer than it was in class today.